discontinuous.
But what, so we wouldn't write the infinite discontinuity?
If you did it algebraically like we just did here, you would not write infinite discontinuity.
You say it's discontinuous.
It's just discontinuous. And this would be your explanation as to why, because it doesn't satisfy the definition. So there were two perspectives on that. You could do it graphically, or you could do it with the limit definition. They ask you to graph it, don't they? Well, they did. And they do say sketch the graph. So after you sketch the graph, you would see that you have an infinite discontinuity. All right. I'm going to do, I did that one, man. I don't know if I should do 33 or not. Yeah, I'll do 33. Damn it. I'm so tempted not to. But I should, maybe. This is one of your homework problems. CX squared. 33. You know what? I think I'll change it just a little bit. No, because now that I think about it, I think I did this. I think I actually did this on camera. Yes. And the next one, number 34, I was like, no, I'm not going to do it. And then I wound up doing it on the video. I think in the video, I'm like, I'll just get you started. And then I wound up saying, nah, forget it. I'll just go the whole way. So I'm going to change this and make this greater than or equal to 5 and x less than 5. So this is a pretty interesting problem. And let me explain what we want. Find C so that f is continuous on negative infinity to infinity. I know this looks ugly, okay? If it's the first time you see anything like this, I know that looks bad, but let's just analyze this graphically first. All right, this is a piecewise function. I have something happening at 5, don't I? To the left of 5, I have something. To the right of 5, I have something. And at 5, I have something. Now, in the last problem, I just plugged in the number and we got an answer, didn't we? If I plug in 5, I'm going to be in the top part or the bottom part? Top part, right? Because this is greater than or equal to 5. And if you plug 5 into this, what will you get? You're plugging 5 in for the x or the c? The x, right? If I plug in 5, what am I going to get? 25, right? Times c plus 10. And what's that? I don't know. We don't know what c is, right? So I'm just going to make it up, okay? I'm going to say that I don't even know if it's positive or negative. I'm going to say I have some point here. And I really do not know how high that is, do I? I don't know where it is. But I do have a point. And then, if I'm bigger than 5, right? Bigger, that's to the right of, I'm going to draw this, aren't I? And what is that if I drew it? A what? It's a parabola, right? X squared. The c in front has an effect on it as far as, I mean, it's still a parabola, right? But the number in front of x squared controls what, how narrow it is, right? And also if it opens up or if it opens down. Do you agree? Yeah. So depending on c, which is what I'm asked to find, I know the right side of this is parabolic. And again, I don't know if it's up or down. So do you want it to be up or down? Up? Okay, it's up. So it does this, and I'm sitting here, I'm like, yeah, I don't know. These are question marks. Like, maybe it does that, right? It might go down. All right, now, if you were to the left of 5, right? To left of 5, you're this. And that's not a parabola. It's a cubic function. Cubic functions look like that or like that, right? It's like this or like this. And you can have little jiggles in it too also, right? So it could do all sorts of things. And I also don't know what happens, like, does this cubic function, I'll do it in blue, does it do this and come right into that? Well, wouldn't that depend on this? right? Doesn't this number c affect it somehow? So I don't even know where this thing meets up, like if they meet together. I don't know that. I just know it's cubic, and it might do this, and it's an open hole from the left because there's no equal sign here. Do you all understand this? From the left, we got a cubic function. From the right, we've got a parabolic function. At 5, we've got a dot. I don't even know where it is. They want us to find the value of c so that this function is continuous everywhere. What does that mean?
Never have to lift your pencil.
Do what?
Never have to lift your pencil.
Yes, they want us to find the c that's going to be perfect. What it's going to do is it's going to move this around just right, shape it just perfectly, and see c is in both equations, right? So it's the perfect c that's going to kind of massage this one around and massage this one around and get them to line up perfectly. Find it. Understand? The question, do you understand? Okay. So does that seem difficult? Yes? It seems like that would be very hard to do, wouldn't it? Doesn't that kind of seem difficult to do? All right, but think about what they're asking for. If you're continuous, if you need to be continuous everywhere, we know for sure, to the left of 5, we are continuous. Why? Because that's a nice continuous polynomial function, right? And to the right of 5, we are continuous. Why? Because it's a nice parabola, right? So the only place we really are interested in is 5, right? So that's what we're going to write down. We need, it's a very strong condition. We need continuity at 5, right? That's what we need. Okay, so if you need continuity at 5, tell me what that means in terms of the definition. We need, good, the limit as x approaches what? 5 of the function to be equal to f of 5. That's what we need, right? That's what we must have happen in order for this to work, right? As that's telling us that as we come in from the left and we come in from the right, that we're going to be headed to the same place. That's the left side of the equation. We'll be headed to the same place, and when we get there, it's going to be the function's value. It's going to be that dot. That's the definition. All right. Working with this, just with that simple equation, we're going to work the left and right-hand sides down. So let's start with the right-hand side because it's easier. What is f of 5? You told me this a second ago. What was f of 5? 25c plus 10. Agreed? That's the right side. Questions? Plugging 5 in, top one? All right. What about the right side? The left side. Limit x approaches 5. There's a critical point right here in the problem.
125.
You can tell me right now that this, just from our drawing and our thinking this through, that this function is left or right continuous. Right now, the way we drew it, right here. It's right continuous, right? And the reason why is because we have the equal sign here, right? So anything bigger than 5, as we come into 5, we're headed to the same place the parabola is headed. So right continuity is already established. What I need is left continuity to happen, right? And then the two of those together would give me the full continuity that I need. Yeah? Yes? Okay, so what I'm going to do at this point is I'm going to change this to left side. Because I'm working with the inequalities in my picture to realize that this is what I'm interested in. Making that side continuous. Now, if you are approaching 5 from the left, what function are we talking about? The top one or the bottom one? The bottom one. Right? The bottom one? Because this is what happens when x is less than 5, right? To the left of 5. So this is going to be replaced right here. X cubed minus cx. And now, you're just going to do a direct replacement. Let x go to 5, right here. And what do you get?
Negative 125.
Careful, x goes to 5, not negative 5. 125. So you get 125, and I'm not writing the limit. Notice that? I'm not writing the limit because I'm applying the limit. 125 minus 5c, and that must equal what? 25c plus 10. And that is a linear equation that you can solve for c. And we're there pretty much at this point.
Wouldn't it be like positive 5 because there's like a minus on the C?
Where? This is positive 5, right?
Oh.
Right? This is from the left side. Careful. All right, solve this equation. I'm going to move that over. I'm going to get 30c equals 115, I believe. Yes. And then divide through by 30. Yeah. I believe we can reduce that fraction. I'll leave that up there. What is it? 23 over 6. Reducing each of these by a factor of 5. Okay? We're there. We're there. What we have done is we have found the c. So if I come back over here to this function and I replace both of those c's with 23 over 6 and 23 over 6, and I were to graph these things, the result should be a parabola that comes into a cubic function, and at 5 they paste together. Now I'm going to prove it to you because I just made up this problem, so I'm putting it all on the line right now. Oh, would someone erase that while I'm doing this? Well, you know what? Hold on. Leave the left side up. Just erase the right side for now. Thank you. Pardon? Yeah, you can get rid of all that. Oh. Oh, come on. Give me a second. This is going to take me just a minute to do. I'll make this a little bigger so you can see what I'm doing if those of you who might be interested. So I'm going to plot, what is it, 23 over 6 times x squared plus 2x. And I'm going to plot that just, what was it? That was if x was bigger than 5, right? So I'm only going to go from 5 to, let's say, 15. All right. A couple of other things I need to throw in here. This is origin. All right, there it is. Do y'all see it? That's it. That's the parabola. Now I'm going to come in here and plot with it x cubed minus 23 over 6 times x. And I'm only going to plot that from, let's say, negative 10 to 5. Understand what I'm doing? Kind of? Yes? And now, with this program, if you're going to do two plots at the same time, you have to add another thing around it that says show, so it'll show them both at the same time. What did I leave? Hold on. Oh, I forgot to put the x. Ah, there it is. Perfect. Can you see it? There it is. Can you tell the difference between the two? You can tell something happened there, right? This was the cubic function coming in, and then right there at 5, it switches over to the parabola. But they're perfectly lined up, right? Perfectly lined up. And that would have been very difficult to do without the idea of the limit.
It actually shows when you plug them both in on here.
Yeah, the values match. Now I'll show you something cool about this program. I'm going to do something a little different. I'm going to go back up here to my code, okay? I'm going to replace this 23 over 6 with c, because that's what it was in the original problem, right? Yeah. And then I'm going to replace this with C. And then I'm going to do this thing called manipulate. And I'm going to allow myself to control the C value between -10 and 10. And watch. There we go. One more thing. What happened? Oh, 2 commas. Okay, so I don't know. I don't like my plot range. You're going to have to bear with me. Does this look complicated? It's starting to a little bit, huh? There we go. Okay, that's a little easier to look at. Got it? So what I can do with this is I can start adjusting C and watch how both the graphs change. You see? See how they both change? So as I tweak the C value, I'm changing the shapes of the graphs. What we were trying to find was that perfect C value that would get those to line up, right? And we found it. It was exactly 23/6. So if I come in here and I put 23/6, there we go. It's right on top. All right? Now, in the problem that you have in the homework, it's the same exact thing, except instead of being at 5 where that break is, it's at 2. But it's the same setup. And then in the next problem, number 34, you actually have three pieces to the piecewise function. And there are 2 variables you're trying to solve for. That's an interesting problem. Watch my video. Watch my video. Yeah. Remember, you won't always see every type of problem that you're going to be faced with in class. So you have to solve a system of equations to do that one. All right. I have 20 minutes. I need to talk about the last concept here. And that is the intermediate value theorem. Now I talk about this again in the video. This is a critically important theorem in mathematics, this intermediate value theorem. But it's a pretty simple idea, right? The idea of this intermediate value theorem. All it says is that if you have a function that connects 2 dots together, right? If it's continuous, if this function is continuous, that I have to draw something from that dot to that dot without picking up my pencil, right? So I have to go from here to here, and it's got to be a function, so it has to pass the vertical line test. So, you know, it could do all sorts of things, right? The intermediate value theorem, all it says is that if the value of this up here is, let's say, this is B, right? Let's just say that's B, and let's just say that's A. Then when I plug B into the function, I get something out, right? We call that f of B. And if I plug something in here, like A, I get something out, f of A. The intermediate value theorem says as long as this is a continuous function, you must achieve every single value between these two at some point. So for example, if this function, let's say the value right here, let's say that was 1, and let's say that was 8, you're guaranteed by the intermediate value theorem that so long as the function is continuous, somewhere in there it's going to be 7. Somewhere in there it's going to be 6. Somewhere in there it's going to be 5. Somewhere in there it's going to be 5.725965443, whatever, right? Every value between 1 and 8 must be achieved by that function. That's the intermediate value theorem. That seemed pretty straightforward? Now, if you're discontinuous, you throw this out the door. Because if you're discontinuous, you could have something like this. So if you look at this, because it's discontinuous, this theorem doesn't work. And you can see right here, there's some values in here, right, that I never get to with the function. So that's why it's a very strong condition. You must have continuity for the intermediate value theorem to work. Yes?
Oh, so if you were just look at a part of that, like from A to I guess like half wherever it is, then it would be intermediate?
Yes, if you just look like from here to here, yes, that would satisfy the intermediate value theorem. Yep. Now, this is good, believe it or not. This is very, very good. But before I get to the last topic, the last problem I'm going to show you, do you know what functions are always continuous on their implied domains? What types of functions are always continuous on their implied domains? I say this in the video. All polynomials. All polynomials are continuous everywhere. If you draw me a polynomial, right, it's either going to be a straight line, it's going to be a parabola, it's going to be a cubic function, or it's going to be some crazy-ass polynomial thing. All of these functions, all polynomials, you can draw without picking up your pencil, which means they're continuous everywhere, right? Which means the intermediate value theorem applies to all of those. Got it? The other things that are continuous everywhere. Rational functions and trig functions and exponential functions and log functions, as long as you're talking about them on their implied domains, which we talked about last week. So when you look at a rational function, everywhere you can draw it, it is continuous. The only places you're going to have problems with rational functions are where you have vertical asymptotes or holes. But everywhere else, it's continuous, which means that everywhere else you would have intermediate value theorem apply. All trig functions and exponential and logs are the same way. So let's use this. We're about to use the theorem. Here we go. Show the equation cosine x equals x to the 5th power has at least one solution. Now let's read this carefully. Show that this equation has at least one answer, right? That's what this wants. Is it asking you to tell us, or is it asking you to actually say what the answer is? No. You all clear with that? It doesn't say find the solution to this equation. It says show me, prove to me that there's at least one answer to this, that there is a solution. Understand the question? All right. Well, so we get all confident in ourselves and we say, well, you know what? I mean, I'm an algebra specialist. I went through pre-cal. I'm good, you know. I should be able to solve this equation. So can you solve this equation? Could you try and solve it? How would you, anyone here want to take a shot at how you would go about trying to solve this? Do you see anything that you could do? It should be confusing. I mean, it should look hard because there is not a way to solve this. And the thing we run into is this. You're trying to solve for x, right? So you eventually need to get x by itself. You need to free it from everything. On the right side, you have x by itself, don't you? So you might be like, oh, I can just take the 5th root of both sides and I'm done, right? Take the 5th root of cosine x, take the 5th root of x to the 5th, and you get x is equal to, well, the 5th root of cosine x. Have I solved for x? No, because in order to know what x is, I have to know what x is. So it's a circular argument, right? You're sitting there needing the information you're trying to find requires the information that you need, and you're never going to get it. Okay, so you come in here like, all right, well, It's that darn cosine that's causing the problem. So, pre-cal, I'll take the arc cosine, or inverse cosine. There's different notations, right? I'll take the arc cosine on both sides. And you're like, that will free the x over here, won't it? So you free the x, and of course there's some domain issues that we might have to worry about, but yeah, but you solve for x, but again, to know x, you have to know what x is, you have to know what x is. So you're still stuck. And there's no way you can do it. It is impossible to solve this equation by hand. Is there a question?
Just start plugging values.
Now you could try to find a value of x by plug and chug, right? Trial and error. And it turns out that there is not a way to do this, okay? There's not a way to do this easily by hand. But there are ways to do it efficiently with calculus and get to an answer, an approximation, right? And this is exactly what your calculators do. All right, so I'm going to go to my computer here, and I'm going to go to Wolfram Alpha, your favorite, right? You like Wolfram Alpha? I think I have enough bars to go to Wolfram Alpha. Come on. I'm going to just type that in. Solve cosine of x equals x to the fifth. Enter. Now, Wolfram Alpha is never wrong, right? Wow. 0.907550. Right? You see that? Bam, that was quick. Do you see the squiggly? What does that mean? Approximation. If you wanted more digits, you could click here and pay $30 a month or something. No, I don't know what it is, but you could get more digits, right? Even Wolfram Alpha has an approximate answer to this. And believe it or not, what they're going to do, what the algorithm, the computer algorithm is doing, is it's first of all using the intermediate value theorem. That's the first thing it does. And then after that, it does something called the mean value theorem. Nope, I take that back. It does something called Newton's method, which we'll get to later on. We have a long way to go before we see Newton's method. But we got to set this up. We'll come back and we'll do this problem later, but we're going to at least answer this. We're going to show it has one answer, okay? So here's what I'm doing. Have I convinced you can't solve it by hand? Yes. Okay. So I'm going to now move everything to one side. Now, do you remember in college algebra when you were looking at parabolas and you wanted to find x-intercepts? How did you find the x-intercepts of a parabola? You take the function and you set it equal to 0, right? And we do that all the time, don't we? If we ever want to know where a function hits the x-axis, we just set the function equal to 0. Yes? So if I'm looking at this right here, if I move that to the other side, and I come in here and I call this right here f of x, then essentially this equation means find the x-intercepts of that function. Right? Find the x-intercepts. So this translates into finding the x-intercepts of the function f of x equals cosine x minus x to the fifth. Now we're going to use a little bit of visual aid. Somebody tell me what f of 0 is. Plug 0 into this function. And what do you get? 1. Does everyone see that? If I plug in 0 here, cosine of 0 is 1. 1 minus 0 is 1 minus 0 is 1. So we get 1. So I know this much. If I graph it, I have this point, right? Now, let's try something else. Where else are you going to be comfortable with plugging something into cosine without your calculator? Like, yeah, what other value, what other angle are you comfortable doing cosine of? 3. You need a calculator for cosine of 1, right? Probably. What other angle Do you know what cosine of pi is? What's cosine of pi?
Oh, no, 0.
Cosine of pi?
Yeah.
Negative 1. Cosine of pi, here's pi, right? Cosine is your x-coordinate. Negative 1?
Yep.
Right? So if I say what's f of pi, you're getting what? Negative 1 minus what?
Sorry.
Did we just find a solution? I think we just accidentally found a solution.
Huh?
What's negative 1 to the 5th power? Negative 1. But then you're subtracting negative 1, which becomes
It's the
plus 1, right?
with or without parentheses.
What, the negative 1 in here?
Yeah.
With parentheses.
Already.
Okay. Hold on a second. I didn't want this to happen. I accidentally just found a solution. That's not what we wanted. Okay, that doesn't, so let me change this. No, I'm not going to. I'm going to do it this way. Sorry. I'm going to do pi over 2. That will never happen, okay? Yeah, negative 1. But then you're subtracting it. So it's plus.
How do you know it was a solution?
Because I was getting 0 out. I was getting I was getting negative 1 plus 1. Oh, it was pi.
Pi to the 5th. Pi.
No. I'm having a brain fart. Okay. Thank you. I'm glad that you called that out. We were okay. I panicked too early there. That means I had a good weekend. All right. Cosine of pi was negative 1. I apologize. Minus, what are we plugging in? Pi. I was plugging in negative 1. I don't know why I did that. To the 5th. That's what you're saying, right? Now that is going to be what?
300.
Some huge negative number, right? Some huge negative number. And actually, I don't even care what it is, okay? All I care, though, about is that it's negative. Why do I care that it's negative? I know that if I plug in 0 into this function, I get positive 1. And if I plug in pi, I get negative something.
So it has
What?
the I.
The intermediate value theorem tells me that if this is a continuous function, I must achieve every value between here and here, right? That means somewhere I must, somewhere, I don't know what this looks like, but somewhere between here and here, I've got to get from this point to this point. So somewhere in there, I have no choice but to pass through the x-axis, don't I? Somewhere. I don't know still, but it crosses through. And if it crosses through, then I have solved this equation. So I know sometimes this can be confusing because it's so obvious. All you're doing is this, taking the equation, moving everything to one side, calling that a function. Then you're picking two values arbitrarily. You have to guess these two values. And what you're hoping for is what? One of these is, and the other one is negative, or the other way around. This one's negative and this one's positive. If you have a continuous function, which this is, why is it continuous? Cosine is continuous because it's a trig function. X to the 5th is a continuous function because it's a polynomial. You put two continuous functions together, you're still continuous. So I know I have a continuous function, and if I go from a positive to a negative between two values, then it must pass through 0. Right? There's no way to go from positive to negative without going through 0. And so that equation has an answer. Yes?
So it didn't have to be like the function at 0, the function at pi. It could have been any number. Just
Any
as
two
long as-
numbers, so long as they change signs. So when you get to a problem like this, you're just going to pick, you're going to guess. And start at 0. You know, start at 1, whatever you want. And you could break your calculator out and try, you know, plugging 1 in instead of pi. All you have to do is show a change in sign. As soon as you show a change in sign, you have shown at least one answer. Now, at least one. There could be more. Yes?
Oh, when you put it in Wolfram Alpha,
Uh-huh.
did it show the cosine of x as a graph and then x to the 5th power as a graph?
It may have. I don't recall. Did it? Which would represent their intersection, right? Yeah, it's looking for that intersection of those two graphs. But see, I didn't look at it that way. I brought everything to one side and looked at that as its own function. Now, I have 5 minutes, so I'll go into this a little more. What did Wolfram Alpha say the answer was? 0.9? 0.9. Okay, so let me do this. I'm going to show you how your calculator, how Wolfram Alpha gets that answer. There's different ways to do it. The way I'm going to show you is the first way ever developed. It's actually not what Wolfram Alpha uses, because what I'm going to show you is too inefficient, but it still works. Okay, it's called the bisection method. You're not going to be tested on this. Think about this. Your calculator, when you type this in for your calculator to solve, what it does is it essentially makes an equation out of it like this, equals 0, and then it just picks 2 points. It plugs them in. So let's say your calculator plugs in the point 0 and pi. Right? Let's say it does. Plugs in 0 and pi. Then your calculator knows you're getting a positive number here and a negative number here, right? So then what it does is it says, okay, I know somewhere in there I have an answer, right? So it cuts this in half, pi over 2. All right? And then it plugs pi over 2 into this. So what happens? You plug in pi over 2. And when you plug in pi over 2, cosine of pi over 2 is 0. And then minus negative pi over 2 to the 5th power. Why did I put negative? That's going to be a positive or a negative number. This is 0, but then minus this number, right? It's going to be a negative number, right?
Oh, because it's never mind. Okay.
Right? So what your calculator knows now is that at 0 it was positive, right? Here at pi it was negative, and at pi over 2 it's also what? Negative. So what does your calculator do now? It cuts that in half and goes to pi over 4. And it tries that. And eventually it's going to move over far enough where it's going to have a value that's positive. Does that make sense? And so what it does is it starts to narrow this window down, because your calculator can do these things, right? I mean, so many thousands of calculations per millisecond. So it starts with an interval and starts to bisect it. And so every time, so like, you know how when I cut it here, there were 2 sections? In this section, we have a change in sign from positive to negative. In this section, do I have a change of sign? Negative, negative? No, right? So the calculator throws that section out. And then it goes to this section, cuts it in half, figures out which section has the sign change, and then takes that section and cuts that in half, and keeps doing that until it refines the number down where your interval is really, really small. Really small. How small? Well, that's whatever the built-in tolerances are on the program. You may say, keep doing this until that interval gets to be the difference between the two numbers is like 0.00000000001, like 14 zeros and a 1. And then what it does is says, as soon as I get to that, take the middle number and spit that out as an answer and put a squiggly equals on it. That's what's happening. So it's called the bisection method. Later on, you get the Newton's method, which is more efficient. It converges faster, doesn't take as many iterations to get to the answer. Okay. I think that's it. I don't think there's anything else. Do your homework. Make sure you watch the homework videos if you need it. We will do 1-6 next time. Please watch the video. I think I like the idea of having quizzes on Wednesdays. Do y'all like that, or do you think you want them more on Mondays? Wednesdays? Yeah? Oh, sign in. I keep forgetting. Let's see. Let me see if these people are here. Angelica? Alan? Isaiah? Maria? Maria, no? And I see. I can't. Okay, I can't. I'm gonna have to work on it. How about Isaiah Rodriguez? Okay. So I have the only person I'm counting absent today is Maria. Okay. Anybody that missed last class? All right. Everybody have a good day. Oh, hold on, I've got a